Okay, so we looked at indefinite integrals, where we ended up getting the plus c, and then also finding what the c value is. And we've also used some of this integration notation. What we're going to look at now is definite integrals, which is very much related, but just requires a few extra steps. So I will explain how you do the definite integral calculation, and then we'll just practice a little bit, and then next session we'll see what it's useful for. But for this session we'll just see how we actually do them and how we actually calculate them. Before we start though, I've got a question here which is not on the topic of integration, but which will be useful for a later example, potentially next session. It's a bit of a revision on inequalities and polynomials, so give this one a go. See if you can remember how to do this. What are the values of x which satisfy the following inequality? If you've forgotten how to answer that, think about drawing a graph. So give it a go. Pause the video now. Okay, so in this case, what we're going to do is first factorize the quadratic, which will then allow us to graph it, which will then allow us to visualize the inequality effectively and assign some meaning to it. So I'm first thinking of splitting this up as follows, with the key values of 5 and 8, because we've got 2 times 20 is 40 and minus 13. It seems like 5 and 8 will allow us to factorize this quadratic. So we end up with the following. And that seems to be working. So the quadratic is the same as this expression here, factorized. Let's not forget the inequality, it's greater than 5. So if we were to plot this part, then we just need to think about a few key things. First of all, where does that cross the x-axis? So that's when y equals 0, or in other words, the output is 0. So the key values, or the critical values, we could call them, are when this becomes 0. So that's when x is equal to 4, because then x minus 4 is 0, and when 2x minus 5 is 0. So that's when x is 5 over 2. So on my graph here, I'm going to mark that on. 5 over 2 is about 2.5. And then to the right of that, we've got 4. And we know that because it's got a positive value before the x squared, it's a U shape rather than an N shape. We could even say where it crosses the y-axis, right? It crosses the y-axis, in this case, at 20. Because that's when x equals 0, we get 20. So the graph looks something like this. Okay, I've just missed the cross there. And the question then is, when is this greater than 5? Right? So when is it greater than 5? It's going to be greater than 5 when it's above this line here. Oops, that's y equals 5. Okay, so we've got effectively two values on the x-axis, one there and one there. We want all the values that are to the right here, and we want all the values that are to the left here. And what we could then do is we could solve the equation y equals 5 and 2x squared minus 13x plus 20, when are they simultaneously true, and we'll get our two x values that correspond to those two ranges. Okay, now what we could do is just do that directly in the first place. So I'm not going to do it that method. I'm going to switch now to a more direct method which will answer this question for us. So instead of solving the version with greater than 5 on the right hand side, let's instead straight away turn it into an inequality which is greater than or less than 0. So that means it becomes plus 15 here, and then it's greater than 0. And this is still minus 13x. Okay, so that's exactly the same question, isn't it? And then let's again factorize the quadratic. And we seem to get the following. Okay, and here our key values are x equals 5 and x equals, so 2x minus 3 equals 0, 3 over 2. We'll draw the graph. Let's put 5 there. 3 over 2 is 1.5. Let's put that there. And again, it crosses the y-axis. Oh, not at 20 this time, sorry, at 15. Okay. And that's our graph there. And effectively, all that is the one we had before, but just shifted down by 5. And likewise, the horizontal line, which we're comparing, it's now not 5, is it? It's y equals 0. So we're looking at the y equals 0 line, which is the x-axis effectively. So for which values is the graph greater than 0? It's these values here and these values here, which corresponds to the following range. Exclude 3 over 2, but take everything to the left of it, and exclude 5, but take everything to the right of it. So our final answer is x is less than 3 over 2 and x is greater than 5. Okay, so let's go back to our main topic of integrals. And what is the difference between indefinite integrals versus definite integrals? So indefinite they look something like this. It's an integral sign of a function with respect to its variable, and the answer is going to be what kind of mathematical object. It's going to be another function, right? It's a function. In other words, or as an example, if you had x cubed, you integrate it, you get a quarter x to the 4, that's just another function. However, with definite integrals, they look as follows. Very similar, except you're going to have two additional numbers, and you're going to put them here, one here and one here. Okay. And the meaning of this will become clear in the next session. We're just going to learn how to calculate this first. So you'll have two additional numbers, and what that means is that your calculation will be a little bit different to the indefinite version, and your answer, instead of getting a function, you're just going to get a number, a single number. Negative or positive, it could be decimal or integer. Okay, I haven't told you yet how to do it, but this is an explanation of how they differ. Indefinite looks like this, definite looks like this. If your answer is a number, you're doing definite integration. If your answer is just another function with a plus c, then it's indefinite. Okay, so let's look at how to actually do a definite integral. Okay, so here are the steps for indefinite integration, and I'm going to follow the steps using a specific example. So let's make one up. Let's say I'm doing the integral of, let's say, 8x cubed. And because it's indefinite, it means there's going to be some numbers, one on the bottom of the integral sign and one on the top. They can be whatever we like. Let's pick, for example, 3 and 4. Okay, so this is a definite integral, and let's learn how to calculate this. How do we get the final answer, which is going to be a number? So the first step is to write the integral with limits. By limits, what I mean is these numbers here. These are our limits. Okay, we call them the limits. Again, why they are given that name will become clear in the next session. But those are called the limits. We've basically done that already. But let's just restate it here to be clear. Okay, that's our integral with the limits. Perform the integration, step 2, and note the limit using square brackets. That won't mean anything to you until you've seen it done at least once. So we're going to perform the integration, meaning just focus on the 8x cubed part. Forget about the 3 and the 4. So 8x cubed integrated is 2x to the 4. And I'm also going to say, as part of this step, ignore plus c. Okay, so when you're doing definite integration with two number limits, don't worry about including plus c, just forget about it. So we get 2x to the 4, and now put square brackets around it. Okay, this is the standard notation. And then those two limits, you're going to put those on the right hand side, again, one on the bottom and one on the top, like this. Okay. And this has a meaning, which is then acted on in the third step. Okay, but that step 2 is basically saying integrate the expression just as you normally would with indefinite integration, and then just place the limits on the outside of these square brackets so that we know what the limits are, so we've kept track of them. Okay, and then the third step is to do the following. Evaluate the function at each limit, each of the two limits, and find the difference. Take one away from the other. So this literally means take that top limit, let's call it the top, and substitute it in as the value for x to get a number. Then do the same with the bottom number. Substitute that for a value as the value of x, get a new number, and then do the first minus the second. So what that looks like is as follows. It's 2 times 4 to the 4. That's the 2x to the 4 with x is 4. And then take away, and it's always a minus, the same function with 3 substituted. Okay. And that will give us our final answer, whatever that may be. 4 to the 4, that's 16 squared is 256. Times 2 is 512. And you're going to take away 2 times 3 to the 4, that's 9 squared, 81. Times 2 is 162. Our final answer, 350. Okay, so our original integral, our definite integral, which we expressed here, has a value of 350. So if we didn't have the limits, the 3 and the 4, the answer we would have written would have been 2x to the 4 plus c. But because we were given some limits, these two numbers, we then do this third step and we put those limits in and we get a number. And in this case it's 350. And that number has a meaning. Again, we'll get to it in the session that follows this one. But for now, we want to practice doing a bit more of this, looking at definite integrals and calculating their values and understanding this process here, which I've laid out in these 3 steps. Okay, so let's look at a couple of examples. This is the first of two. So we're being asked to evaluate this definite integral. So first step, write it with the limits. It's already been done for us. I'm just going to write it again. And then second step is we're going to have to perform the integration. Now, in this case, we can't do the integration until we've multiplied out the brackets, so that it's just a single set of terms without squaring the whole thing. So let's do that. I'm going to keep the integral sign with its limits the same, and we're going to do x to the third minus 1 all squared. So effectively I'm doing this, which gives me x to the 2/3 minus 2 lots of x to the third plus 1. Okay, now we can perform the integration. So because we're about to perform the integration, let's get our first square bracket ready. Add 1 to the power of the x to the 2/3. We get 5/3 divide, and this we all know how to do. We've done plenty of it in the previous session. So 1/3 plus 1, that's 4/3. So multiplying by 6 over 4x to the 4/3 plus x. And as I said, forget about the plus c, just close it off with another square bracket and put the limits there. So we've got the 0 and the 1. I'm just going to change that 6/4 to a 3/2 because that simplifies. Okay, and now we're going to substitute the two values in. The way I tend to do this is I create two sets of round brackets, and we can switch to the round ones now. And in this one, I'm going to put my top limit, and in this one, I'm going to put my bottom one. So the top limit is 1. So work out what is this whole expression when x is 1. Well, the powers are not going to make any difference. 1 to the power of anything is 1. So we get 3/5 minus 3/2 plus 1. And when I put in 0, I'm actually just going to get 0, aren't I? If I put 0 in this function, it all just cancels out. That's not always going to be the case, but in this case it will give me a 0. So I end up with just the 3/5 minus 3/2 plus 1. Okay, and then we work that out, and that should give us 1/10. So that's the value of that definite integral. We get a number, and it's 1/10. Okay, so let's look at the second example, and this one has a few more unknown quantities in it. Again, what's actually happening here and what kind of question this actually is, at this stage it's all a bit of a mystery. It's mainly just about doing the calculations. So this is, at this stage, very pure, very, I suppose, obscure mathematics, but it will definitely have an application, and we'll start seeing that soon. But let's make sure we know how to actually answer this question in its purest form. So you've been given a definite integral, and we know it's definite because it has the limits. In this case they're 1 and 5, and there's also some unknown constant p within the integral in addition to the usual variable x, and we're told this thing on the left, this definite integral, is apparently equal to 4p squared. Show that there are two possible values for p and find these values. So we don't really need to understand what this really means or where these underlying values have come from. We just want to be able to do the calculation. So what we're going to do is the left-hand side first, and we're just going to treat p as a number, and you do the same steps that we just did a moment ago. So I'm going to write it out again. It's the integral from 1 to 5 of 2px plus 7 dx, and I don't really need those brackets. What's that equal to? It's I can integrate that, so I'm going to start with my square bracket and perform the integration. The integral of 2px, well, that's x to the 1. If I add 1 to the power, I get x squared, and I divide by 2, I end up with capital P x squared. 7 goes to 7x. Forget about the plus c because we're doing definite integration. Close it off with another square bracket, put the limits on the outside. Okay, let's now do the top substituted in minus the bottom substituted in. Replace x with 5 and we get 5 squared 25p, and we get plus 7 times 5, so plus 35. That's the top. And then the bottom is when I substitute in this 1 into here, where x is the thing that I'm substituting the 1 as. So that's p times 1 squared plus 7. In other words, p plus 7. And now be very careful when we say take away, find the difference, you need these brackets here. This is minus p and also minus 7. It's not just a minus of a p. That's a very easy mistake to make, to not apply this minus to everything inside these terms, inside those brackets. So 25p minus p is 24p. 35 minus 7 is 28. Okay, so that left-hand side we've shown is the same thing as 24p plus 28. And remember, that's just a number. It's not actually a function. It's a number because p is a number. We just don't know what p is yet. Okay, and then the question says that all of that is apparently equal to 4p squared. And what we've got here effectively is a quadratic. And that therefore explains why there's two possible values, because any quadratic with real solutions, unless it's a single duplicated solution, is going to have two answers, two solutions. So let's first divide by 4, just to simplify that a bit. Do some rearranging. And we've got it in the form of a quadratic. In this case, is it obvious how that factorizes? That factorizes to p minus 7 times p plus 1. And that tells us p is equal to either minus 1 or 7. Yeah, and that's it. That's the answer there. Okay, so no idea what p is. The question doesn't in any way tell you what p actually means or provide any visualization to what's going on, but you should be able to answer a question like this. It's just algebra and applying the steps that we've talked about. So let's see if you can do some yourselves. So here are the questions I'd like you to try. They're all on this slide. Question 3, 4 parts. For all of those, your final answer is just a single number. And then you just want to check that number in the back of the book, see if you get it right. Question 4 is similar to the example we just did. You've got a constant in there. In this case, it's a capital A. And you're going to find what those two values for A could be, presumably because there'll be a quadratic. Question 7 is going to do something which we haven't looked at yet, but you should be capable of doing. One of the limits is not a specific number. In this case, the bottom limit is 1 and the top limit is a constant k. But just do the steps as you normally would, except instead of a number, you're just using the letter k, just as you would with algebra. See if you can figure out what k ends up being. And then finally, there's a challenge question here where you actually end up with both limits being expressed in terms of a constant. And you can see if you can have a go at that one if you dare. Okay, so give those a go. Check the answers once you've given them a genuine attempt. You can pause the video now.